All right. So like I said, lots of terms and definitions. The assignment for today is very, very brief. It's just kind of applying your interpretation of those definitions, picking out information from some diagrams. So pretty laid back first day, in my opinion, after we get through this dull set of definitions. So the first one we have here, kind of the bare essential of what we need in order to do anything in geometry, which is a point. So a point is a location with no size or shape. Simply describes a location. There is no actual physical object. You can't touch it, see it, which is confusing because the visual I'm about to give you, we're actually drawing something. A little weird, but it's hard to imagine things are there if we can't actually see them. So typically when we are representing points, we just use dots. So I'm just going to go ahead and put 3 points on here. I'm going to label them A, B, and C. And that's going to be something that becomes pretty common because we're going to be dealing with lots of points. Being able to describe to each other which points we're talking about, we typically label them with letters. So I have 3 points here, A, B, and C. Again, some of you are thinking, Josh, that looks like a circle. Yes. And that has a size. Some of those are a little bit bigger than the others. That's where some of the confusion comes in. Those points are just describing locations. Because of our limitations as human beings and our eyesight, we have to draw something that's still visible for us to be able to work with. Again, at any point, feel free to stop me if I say something, do something, write something that you're a bit confused about. All right. What's gonna be really great is when recording in progress is in the actual recording, if anyone watches this later. Oh well. When I first started recording lessons a long time ago, I thought, oh my gosh, it has to be perfect, it has to be professional level. And then I realized I'm killing myself for something that I'm not even qualified to do. So all the videos I posted for Algebra 1 are completely laid back and just, they serve a purpose. They're not perfect, but they help. So, oh well. Next on our list here is line. So a line is made up of points. I'm actually going to say is made up of infinitely many points. And has no thickness or width. So again, if you've been in algebra, you've worked with lines. What we do with them, some of it will cross over from what you've already experienced, but some of the stuff we're going to do with them is a little bit new as well. So an example of a line, drawing a line here. It's important to have arrows on both ends. I'll talk about why that's significant here in just a moment. But typically to denote it, we usually identify 2 points on that line. So in this case, I'm going to have points X and Y, because in mathematicians, especially in geometry, really like to abbreviate when they describe things. So the notation we would use in, say, if we were writing a paragraph describing the math, to describe this particular line is we would write the letters X, Y, with a little line written above it. So if I was writing a paragraph and I said line XY, I wouldn't actually write the words line XY. I would denote that symbol. Again, not expecting all this to be memorized. That's what the notes are for. Quick recall. Now, the next one on here emphasizes why it was so important to put the arrows on the ends of our line, because we also now are going to start working with line segments. So line segments are just a measurable part of a line. Consisting of two endpoints. So where the line is infinitely many points and it goes on forever and ever and ever in both directions, a line segment has a starting point and an ending point. It does not go on forever and therefore can be measured to have a particular length. So I'll draw 2 points here. I'm going to connect them with a segment. I'm going to label them R and S. And the little subtext notation that we would use if we were describing this written out, we would use the 2 points identified on that segment, and we would draw a little line segment above it. Notice, again, very minor differences, but they represent very drastically different things. Next on our list is a ray. A ray is just a line that extends indefinitely, so forever, in only one direction. A line that extends indefinitely in only one direction. So our little diagram for a ray. Again, I'm going to start by putting 2 points in my space here. I'm going to label them E and F. I'm going to start at E. I'm going to go all the way through F and put an arrow showing that that continues on forever. So E, it's kind of like the starting point. It doesn't go past it, but then it continues on through F forever. Now, to denote this, here we have to be a little bit more careful because we do have one direction that goes on forever. Our little notation, you have to have the arrow on the side that matches the point through which it passes through. Does that make sense? So the arrow is on the side with the F because it goes through the F and goes on forever. If I'd spun that around, I would be describing an entirely different ray. One that started at F, went through E, and continued on forever in that direction. So this one's probably the trickier one because it's a little bit more specific to the diagram itself. So far, these should mostly be familiar. I would say ray is probably the one that's a bit more new. It's not one that we typically use very often. But so far, we started with points, which have no size or shape. Lines are just a string of points together, which have a length. but no width or thickness. Now we're going to expand to another dimension. We're going to add a second dimension by referring to what's known as a plane. Excuse me. So a plane is a flat surface made up of points and extends indefinitely in all directions. Emphasis on all. So whereas a line was a very specific set of directions for those points to be connected on, a plane now goes and adds not only length, but width. Now here is where your artistic abilities are going to be tested, mine as well. Because drawing lines isn't too difficult. Drawing things with a little bit more depth to them gets a bit unique. So I'm going to go ahead and draw. I don't want it to be just a boring square, so I'm going to kind of draw at a slant here. And to show that this plane doesn't just stop at those edges, I'm also going to draw at the edges of each little extending arrows here to say that this plane continues on forever in each of those directions. So this is just a little snippet. So imagine if I had a sheet of paper on this wall here. This sheet of paper is a plane, but the wall itself is an even bigger plane, and the wall is part of an even larger plane, assuming that this wall continued to grow forever and ever and ever. So again, we start to dabble with the idea of forever, which as humans is kind of a deep concept to think about. And on this plane, there could be all sorts of things. There could be points. So point J, point K. There could even be points that form a line. So M, N. You can have all sorts of things on the plane. You can have points, you can have lines, anything prior to what we've talked about with this plane. So lines only have a length. Well, a plane has length and width, so a line can fit on it. Points have no shape or size, so they can fit anywhere on the plane. All sorts of things can fit on a plane. Next one here, getting into some very specific relationships now with these prior terms, is this term referred to as collinear. Any guesses what collinear would mean? On the same line. So not just any old lines. In order for things to be collinear, they have to exist on the same line together. So collinear are points that lie on the same line. Now, there is a converse of that. So points that lie on the same line are collinear. There is also a phrase referred to as non-collinear. Are points that are not on the same line. excuse me. So an example of this over here in a diagram, I'm going to draw a line here. I'm going to put 3 points on that line. A, B, C, but I'm also going to put a point over here off the line and label it D. Are all those points collinear? Which ones are collinear? A, B, and C. And no matter how hard we try, is there any way I could make that line also pass through D? No, lines don't bend or curve or do anything like that. They go on forever in their set direction, which means D would not be collinear. So we would say A, B, and C are collinear. Not D. Now, theoretically, if I were to draw a second or third line, could I draw a line where A and D were collinear? But only A and D would be collinear. You're right. So if I were to change the line, I might be able to get D to rest on that line with one of the others, but there's no way I can get all of them because of where they're located to exist on the same line. So there are just some things that you cannot make happen as much as you'd like them to. So using an example, using your word roots there, or your clues, what do you think coplanar means then? Existing on the same plane. So coplanar are points that lie on the same plane. If you want to add to that one, non-coplanar would be points that don't exist on the same plane. That one's a little bit harder to imagine because now we start to get into three-dimensional space, which drawing 3 dimensions nicely on 2-dimensional surfaces like paper get a bit tricky. But I'm going to cheat here real quick and steal my plane from earlier. But I'm going to make a few minor adjustments. So J, K, and L in this case are coplanar. I'm going to do something, again, bear with me as my drawing is probably trash. I'm going to draw in a plane going a different direction. Would N be considered coplanar as well? No. Now again, it's on a sheet of paper, so technically we could argue, well, technically they're all coplanar because they're all on the same sheet of paper. And I would say, well, yes, but this requires a little bit of imagination. So imagine, for example, if you were to try to represent this in real life, if I were to draw 3 points on this piece of paper, 3 points on this piece of paper, are these both planes? And no matter where I move them, those 3 points on each respective sheet of paper would still be coplanar, but there's no guarantee and there may be no possible way of making all 6 coplanar without them existing on the same plane. Now I could get something real tricky and maybe get them to intersect one another, but the odds of them intersecting all 3 points on the opposite plane are probably highly unlikely. So this gets a little bit deeper because now we're trying to imagine this third dimension, because we had points which had no dimensions to them. We added lines which had just length. We added planes which now have width. When you start to add multiple planes together in the same space, now you've added depth. I'm not an artist, so my diagrams typically look rough, but we're doing our best to represent these rather intricate scenarios on a limited space. Yes. That's a great question. If we don't get through all of them, then we'll have part 2 tomorrow. Yeah, so, and that's another thing that as we fine tune geometry a little bit this term, some days may roll over to the next day. If that happens because of my poor planning, bonus for you guys, because that just means no assignment today. Shucks, right? But no, there's enough time in this term, we'll cover everything we need to. How efficiently they're packaged, well, that's up in the air, but good question. Next one, congruent segments. Congruent segments, we're going to do an if statement, an if-then statement that says that if two segments have the same length, then they are congruent. Now, some of you might be thinking, well, congruent, isn't that basically saying equal? Yes, in a manner of speaking, but we typically refrain from using just equal because we use a lot of that in algebra with equations. Congruent is a bit farther reaching. We can now say all sorts of things are congruent and not just talk about some equation. So an example here, along with some notation, I'm going to draw two segments going different directions. I'm going to draw segment AB and segment CD. And I think they're pretty close to the same length. I didn't actually measure them, but for our note's sake, I'm going to list right next to each of them that they are both 7 inches long, which we all know is not possible, which is why it actually leads me to a side comment. In geometry, never trust the picture completely. If two things appear to be the same length, do not assume that they are unless somewhere it is either stated that they are or you can prove that they are. Yes, sure. Now, there are two ways to denote it. One is going to seem pretty familiar to us, and that's just to say that AB equals CD. But in our brain, in our algebra part of our brain, we're thinking, oh, should I try to solve for something here? Not necessarily, which is why in geometry, we typically use a slightly different format to say that segment AB is congruent, and the congruent symbol is an equal sign with a, that was terrible, with a little squiggle above it, is congruent to segment CD. So if I had to pick, I would pick that one because we're going to try to stick with geometry mode as much as possible in this geometry class. So it is saying that they are of equal length, but in geometry terms, we would say segment AB is congruent to segment CD. First page done. Again, lots of terminology here, but the goal is to have it all in one spot. So later on in later lessons, I say, hey, are these two lines congruent? You know, what's he talking about congruent, or what's that symbol even? This is going to be our go-to. Okay. All right. This next one, we're going to probably spend a little bit more time later on, but it's, I don't want to say it's an easy thing, but it's something that we probably take for granted. Something we'd be like, oh, that kind of makes sense. I just wouldn't have described it that way. And that is the segment addition postulate. So it reads, and our diagram is going to match this statement here in just a moment. It reads that if A, B, and C, which are points, so A, B, and C are collinear, which means what again? On the same line. So our collinear points, and B is between A and C, then we can make the following statement. We can say that segment AB plus segment BC must equal segment AC. In science, usually when we would describe the same relationship, we usually use the phrase, the sum of the parts equals the whole. So if you go and order a pizza and it's been cut into 8 equal slices, the sum of each slice added with the other equals the sum of one whole pizza. Now, a visual looks a little bit nicer here, so I'm going to draw a longer segment. I'm not going to put any specific measurements here because regardless of what the lengths actually are, this postulate still holds true. So in this case, AB plus BC equals the entire segment AC. So this little piece right here attached to this bigger piece right here equals the entire large segment. Again, it doesn't feel groundbreaking or anything like that, but we've never had to describe it this way before. Again, don't hesitate to stop me if I say something, draw something, anything like that, or just general questions, you know, related to what we're doing. The next two are actually formulas. We're going to write them down for now, but we'll actually spend an entire day or most of an entire day working on using them. And that is the distance formula and the midpoint formula, both which have to do with points on a plane, measuring specific things regarding points on a plane. So the distance formula is the formula, as its name probably suggests, used to find the distance between 2 points. I'm going to say on a coordinate plane because that's usually where we do these measurements. Coordinate plane, you should have heard that term before, especially if you've had me. Coordinate plane is just going to be that grid where we count our X and Y coordinates to find those points. So the formula used to find the distance between 2 points on a coordinate plane. Now the actual visual is going to be the formula itself, no pictures or anything here. If we were doing a picture, it would probably be if we were trying to prove or discover the distance formula, which if you're math inclined and curious as to where it came from, I will gladly share it with you. Most people typically are just satisfied with the formula itself. So D, which is the distance, equals the square root, big square root, of x2 minus x1, that difference squared, plus y2 minus y1, that difference also squared. And that is between two ordered pairs, x1, y1, x2, y2. Which means if you're going to use the distance formula successfully, you are going to need to know their coordinates. Now, just a quick check. Has everyone in here passed Algebra 1? Have you all passed Algebra 2? Well, that's good. So this, again, a lot of this should feel a little bit awesome. So good news is formulas and solving equations are all going to feel just like old stuff. So hopefully then you guys are familiar with what I mean by coordinates, ordered pairs, things like that. Hopefully shouldn't scare anybody too much. Next one here is referred to as the midpoint formula. This is the formula used to find what's known as the midpoint between two endpoints. I'll explain that here in just a moment. So what I use the definition with a term that actually is part of the term itself, midpoint. Any guesses as to what a midpoint is? The middle. That's probably the best summary to say it's in the middle, meaning that if you were to draw a segment from one endpoint to the other, the midpoint would be exactly in the middle on that same segment, meaning if you were to measure the two halves, they would be equal, which halves by definition must be equal. That's how they're halves. But yeah, they're right there, right in the middle on that segment. Now, the midpoint formula is a bit unique. It doesn't quite look like formulas that we're used to because the formula is actually in two parts and it gives us an ordered pair, not just one singular value, because a distance is just a measurement. A midpoint is another point, which means we need to be able to describe where it's located. So the midpoint formula actually gives us an ordered pair. So I would like you to try to use your imagination with me here. We're going to label the midpoint M. But in our giant ordered pair here, to find the x coordinate, we're going to take the two x coordinates of our endpoints and divide it by 2. That would give us our x coordinate. Then to find our y coordinate, we would add the two y coordinates by 2. Excuse me, add them together, divide them by 2. Now, if you wanted to boil it down to the really kind of neat simplicity of that is, technically you're finding the average of the two coordinates. You're averaging, because if you find an average, you add everything up, divide by how many there are. You're finding the average of your x coordinates, the average of your y coordinates, and it just so happens mathematically that lands you on the exact midpoint of that segment. It's really in its simplicity, but then when you look at it in this grand scheme of its complexity, it's kind of, I love it. I get too excited though. Next up, segment bisector. A segment bisector could be a couple different things that are achieving the same goal. Is either a segment, line, or plane that intersects a segment at its midpoint. Now, I'm about to throw a few more little notations at you. Just little intricate things, little subtle details that we use in geometry that will come up more frequently later. Make notes of them as you see fit now to help you feel more comfortable when it happens later. So I'm going to do just very briefly here. I'm going to try to sketch just a regular old line here. And on that line, I'm going to focus on a particular segment, AB. And for the sake of just simplicity, I'm going to try to eyeball where the midpoint is. I'm going to label that M. And then I'm going to draw a second line. And I'm going to label it something we haven't done quite yet with a cursive lowercase l for just line. So typically when we refer to lines, we usually put 2 points on that line with a line symbol above it. Occasionally, especially if you're not terribly interested in that line particularly, you can use a lowercase cursive letter to represent that line as a whole. If you're not interested with anything actually on that line, it makes it more simple to refer to. Again, if you're like, what? It'll come back up again later. There's one other little detail I want to throw in there as well. Now I know I labeled what I called the midpoint with M, which is pretty clear, but there's another notation that would solidify this statement so that we don't make assumptions, because as I mentioned earlier, do we trust our diagrams in geometry? No. And that's not because we should just doubt everything in here. That's because unless it has clearly been stated, shown, or you can prove it, never assume it. So right now, yes, I labeled that point there of the intersection with M. We can assume I meant midpoint, but in order for that to be the midpoint, the distance from A to M and M to B would have to be equal. There's a cool shorthand way to show that they are in fact equal, so there's no guessing. And it has to do with putting a little crosshash mark on each of those segments. So I put a little notch there on AM, a little notch there on MB, because they have the same number of notches. That means that those two segments are congruent. And now we believe it because I said it was. Again, takes a little bit of faith in geometry. We don't want to just believe everything, but then when someone says this is in fact true, or I need you to assume this is true, then it's okay. So a bit strange. Those notations will come back again later. So if you're like, that's a whole lot of stuff all at once, it's okay. We cover this multiple times. Next on our list, this one should not be a stranger to us. This is something that came up in Algebra 1, maybe a little bit in Algebra 2. I don't know. I haven't taught Algebra 2 here. It's been a long time since I've taught it. But perpendicular are two lines or segments that intersect at a right angle. Does anyone know the measure of a right angle? 90 degrees. There is a symbol that we use for perpendicular because one, saying or spelling perpendicular gets cumbersome. There is a symbol that we use for perpendicular, and if you've had me in Algebra 1, I've introduced this to you as well. And that is what looks like an upside down capital T. That is a symbol saying, you put that symbol down, it is in essence saying perpendicular. What follows after that is based off of what you're trying to describe. So an example over here. I'm going to draw some pretty nondescript. I'm going to label this with the lowercase l. I'm going a perfectly vertical line and then a perfectly horizontal line, which I'm going to label with a lowercase cursive m. And again, right now, you are assuming it's perpendicular until I put this little symbol in there. Little box right in the corner where they intersect. That symbol means that this is exactly 90 degrees, therefore a right angle. And if that is the case, the notation we would use is we would say that line L is perpendicular to line M. You're going to notice probably pretty quickly that geometry is a lot of shorthand, a lot of symbols, a lot of very brief notation. Again, you are not expected to memorize all of this today. It's just more of exposure, just to see it. So when you see it again, you're like, ah, that's a thing. And I remember it's a thing. I just need to learn more about it. I think my goal for today is to get these last two in here and then just kind of summarize, make sure we're all on the same page, and then we will pick up tomorrow. Should be able to knock this out tomorrow with time to knock out the assignment as well. All right, perpendicular bisector. This one's a little bit more involved because it's doing a couple things. This is when you have a line segment or ray perpendicular to a segment at its midpoint. So not only is it intersecting in such a way that it forms 90-degree angles is intersecting exactly through that segment's midpoint. So off to my diagram here, I'm going to do a horizontal segment. I'm going to call it AB. I'm going to try to eyeball the midpoint here best I can. From there, I'm going to draw a second segment that's going through it. I'm going to label it, I don't know, CD. And right now we can make some assumptions, but until I put some extra little notation in there, we have to be careful. So here, to say that they're perpendicular, I'm going to put a little box there in the corner. So I know that that is exactly 90 degrees. And so that I know that M is in fact a midpoint of AB, I'm going to put this time, I'm going to put, just to mix it up, just to show you the variety of it, I'm going to put little double hash marks on each of those segments, meaning that AM is congruent to MB. Last one here, and then I think we'll call it for a first day. I think we covered quite a bit. Last one here is parallel lines. These are two lines that never, emphasis on never, intersect. In fact, we could go even further and say they never get closer, they never get further away. If you throw back to algebra days, there was a reason for that. They're going the exact same direction, which meant they had the exact same slope. Now, one thing I did not share with you in Algebra 1 is that there is in fact a symbol for parallel as well. And we will use that much more heavily in geometry. But the reason I didn't introduce it in Algebra 1 is because of the way it looks. It's very deceiving. What does that look like? It looks like an 11. It's not. You got to be careful. But if you think about it, if you have two perfectly vertical lines, those are parallel. Sorry? To show that they're parallel. But then what does it look like? Then it looks like an equal sign. Unfortunately, there's no winning with parallel lines for some reason. At a slight slant, well, then you have to trust yourself to, I don't know. Someone out there far smarter than me came to this decision. I just go along with it. Quick diagram to go though with this before we go our separate ways is I'm going to draw two lines. I can cheat because I can copy this line. So I know for a fact that they're parallel because they are the same line, just moved. Two of the same lines, I'm going to label them lowercase l, lowercase m, because the lines themselves specifically aren't as important as the relationship they share with one another. Right now, though, again, we can't make the assumption that they are parallel unless someone tells me that they are. Now, unlike perpendicular, where we put a little box in it, there's not really one that we put on the diagram itself. Normally, it's a subtext listed somewhere that would look something like this. L is perpendicular to M. If you see that symbol somewhere, then we now know and accept and believe that these two lines are in fact parallel. Did I say parallel before, or did I say perpendicular? Did I say perpendicular? Parallel. I meant parallel. All right, so we're going to pause there for today. So technically, we're slightly ahead of schedule, but I think that's fine. Tomorrow, we should be able to fly through the rest of this because we won't have to go through the syllabus. I will be more set, ready to go. And then the video that goes along will just be a continuation of where we left off.